A nantenna is a nanoscopic rectifying antenna, an experimental technology being developed to convert light to electric power. The concept is based on the rectenna, a device used in wireless power transmission. A rectenna is a specialized radio antenna which is used to convert radio waves into direct current electricity. Light is composed of electromagnetic waves like radio waves, but of much smaller wavelength. A nantenna is a very small rectenna the size of a light wave, fabricated using nanotechnology, which acts as an antenna for light, converting light into electricity. It is hoped that arrays of nantennas could be an efficient means of converting sunlight into electric power, producing solar power more efficiently than conventional solar cells. The idea was first proposed by Robert L. Bailey in 1972. As of 2012, only a few Nantenna devices have been built, demonstrating only that energy conversion is possible. It is unknown if they will ever be as cost-effective as photovoltaic cells. An antenna is an electromagnetic collector designed to absorb specific wavelengths that are proportional to the size of the nantenna. Currently, Idaho National Laboratories has designed an antenna to absorb wavelengths in the range of 3 to 15 micrometers. These wavelengths correspond to photon energies of 0.08–0.4 electron volts. Based on antenna theory, an antenna can absorb any wavelength of light efficiently provided that the size of the antenna is optimized for that specific wavelength. Ideally, nantennas would be used to absorb light at wavelengths between 0.4 and 1.6 micrometers because these wavelengths have higher energy than far infrared and make up about 85% of the solar radiation spectrum. History of nantennas. Robert Bailey, along with James C. Fletcher, received a patent in 1973 for an electromagnetic wave converter. The patented device was similar to modern-day Nantenna devices. In 1974, Gustafson and co-authors demonstrated that these types of devices could rectify even visible light to DC current. Alvin M. Marks received a patent in 1984 for a device explicitly stating the use of submicron antennas for the direct conversion of light power to electrical power. Marks's device showed substantial improvements in efficiency over Bailey's device. In 1996, Guang H. Ling reported resonant light absorption by a fabricated nanostructure and rectification of light with frequencies in the visible range. In 2002, ITN Energy Systems, Inc. published a report on their work on optical antennas coupled with high-frequency diodes. ITN set out to build an antenna array with single-digit efficiency. Although they were unsuccessful, the issues associated with building a high-efficiency antenna were better understood. In 2015, researchers fabricated a solar energy collector that can convert optical light to DC current. Bharatim Kola, a professor at Georgia Institute of Technology, led the team that developed this optical rectenna using carbon nanotubes. The team grew vertical arrays of multi-wall carbon nanotubes on a metal-coated substrate. The nanotubes were coated with insulating aluminum oxide and altogether capped with a metal electrode layer. The small dimensions of the nanotubes act as antennae, capable of capturing optical wavelengths. The MWCNT also doubles as one layer of a metal insulator metal tunneling diode. Due to the small diameter of MWCNT tips, this combination forms an ultra-fast diode that is capable of rectifying the high-frequency optical radiation. The overall achieved conversion efficiency of this device is around 10–5%. Nonetheless, Nantenna research is ongoing. Future efforts have been undertaken to improve the device efficiency by investigating alternative materials, manipulating the MWCNTs to encourage conduction at the interface, and reduce resistances within the structure. Theory of nantennas. The theory behind nantennas is essentially the same for rectifying antennas. Incident light on the antenna causes electrons in the antenna to move back and forth at the same frequency as the incoming light. This is caused by the oscillating electric field of the incoming electromagnetic wave. The movement of electrons is an alternating current in the antenna circuit. To convert this into direct current, the AC must be rectified, which is typically done with a diode. The resulting DC current can then be used to power an external load. The resonant frequency of antennas scales linearly with the physical dimensions of the antenna according to simple microwave antenna theory. The wavelengths in the solar spectrum range from approximately 0.3 to 2.0 micrometers. Thus, in order for a rectifying antenna to be an efficient electromagnetic collector in the solar spectrum, it needs to be on the order of hundreds of nanometer in size. Because of simplifications used in typical rectifying antenna theory, there are several complications that arise when discussing antennas. At frequencies above infrared, almost all of the current is carried near the surface of the wire, which reduces the effective cross-sectional area of the wire, leading to an increase in resistance. This effect is also known as the skin effect. From a purely device perspective, the IV characteristics would appear to no longer be ohmic, even though Ohm's law, in its generalized vector form, is still valid. Another complication of scaling down is that diodes used in larger-scale rectennas cannot operate at THz frequencies without large loss in power. The large loss in power is a result of the junction capacitance found in PN junction diodes and Schottky diodes, which can only operate effectively at frequencies less than 5 THz. The ideal wavelengths of 0.4–1.6 micrometers correspond to frequencies of approximately 190 to 750 THz, which is much larger than the capabilities of typical diodes. Therefore, alternative diodes need to be used for efficient power conversion. In current antenna devices, metal insulator metal tunneling diodes are used. Unlike Schottky diodes, MIM diodes are not affected by parasitic capacitances because they work on the basis of electron tunneling. Because of this, MIM diodes have been shown to operate effectively at frequencies around 150 THz. Advantages of nantennas. One of the biggest claimed advantages of nantennas is their high theoretical efficiency. When compared to the theoretical efficiency of single-junction solar cells, nantennas appear to have a significant advantage. However, the two efficiencies are calculated using different assumptions. The assumptions involved in the Nantenna calculation are based on the application of the Carnot efficiency of solar collectors. The Carnot efficiency, eta, is given by where T cold is the temperature of the cooler body and Thot is the temperature of the warmer body. In order for there to be an efficient energy conversion, the temperature difference between the two bodies must be significant. RL. Bailey claims that nantennas are not limited by Carnot efficiency, whereas photovoltaics are. However, he does not provide any argument for this claim. Furthermore, when the same assumptions used to obtain the 85% theoretical efficiency for nantennas are applied to single-junction solar cells, the theoretical efficiency of single-junction solar cells is also greater than 85%. The resonant frequency of an antenna can be selected by varying its length. This is an advantage over semiconductor photovoltaics, because in order to absorb different wavelengths of light, different band gaps are needed. In order to vary the band gap, the semiconductor must be alloyed or a different semiconductor must be used altogether. Limitations and disadvantages of nantennas. As previously stated, one of the major limitations of nantennas is the frequency at which they operate. The high frequency of light in the ideal range of wavelengths makes the use of typical Schottky diodes impractical. Although MIM diodes show promising features for use in nantennas, more advances are necessary to operate efficiently at higher frequencies. Another disadvantage is that current nantennas are produced using electron beam lithography. This process is slow and relatively expensive because parallel processing is not possible with E-beam lithography. Typically, E-beam lithography is used only for research purposes when extremely fine resolutions are needed for minimum feature size. However, photolithographic techniques have advanced to where it is possible to have minimum feature sizes on the order of tens of nanometers, making it possible to produce nantennas by means of photolithography. Production of an antenna. After the proof of concept was completed, laboratory-scale silicon wafers were fabricated using standard semiconductor integrated circuit fabrication techniques. E-beam lithography was used to fabricate the arrays of loop antenna metallic structures. The Nantenna consists of three main parts: the ground plane, the optical resonance cavity, and the antenna. The antenna absorbs the electromagnetic wave, the ground plane acts to reflect the light back towards the antenna, and the optical resonance cavity bends and concentrates the light back towards the antenna via the ground plane. Lithography method. Idaho National Labs used the following steps to fabricate the Nantenna arrays. A metallic ground plane was deposited on a bare silicon wafer, followed by a sputter-deposited amorphous silicon layer. The depth of the deposited layer was about 1/4 of a wavelength. A thin manganese film along with a gold frequency selective surface was deposited to act as the antenna. Resist was applied and patterned via electron beam lithography. The gold film was selectively etched and the resist was removed. Roll-to-roll manufacturing and moving up to a greater production scale. Laboratory processing steps, such as the use of electron beam lithography, are slow and expensive. Therefore, a roll-to-roll manufacturing method was devised using a new manufacturing technique based on a master pattern. This master pattern in effect mechanically stamps the precision pattern onto an inexpensive flexible substrate and thereby creates the metallic loop elements seen in the laboratory processing steps. Using this semi-automated process, Idaho National Labs has produced a number of 4-inch square coupons. These coupons were combined to form a broad flexible sheet of Nantenna arrays. Atomic layer deposition. Researchers at the University of Connecticut are using a technique called selective area atomic layer deposition that is capable of producing them reliably and at industrial scales. Research is ongoing to tune them to the optimal frequencies for visible and infrared light. Proof of principle. The proof of principle for Nantennas started out with a 1 square centimeter silicon substrate with the printed Nantenna array filling the area. The device was tested using infrared light with a range of 3 to 15 micrometers. The peak emissivity is found to be centered at 6.5 micrometers and reaches an emissivity of 1. An emissivity of 1 means the Nantenna absorbs all of the photons of a specific wavelength that are incident upon the device. Comparing the experimental spectrum to the modeled spectrum, the experimental results are in agreement with theoretical expectations. In some areas, the Nantenna had a lower emissivity than the theoretical expectations, but in other areas, namely at around 3.5 micrometers, the device absorbed more light than expected. After a proof of concept on a stiff silicon substrate, the experiment was replicated on a flexible polymer-based substrate. The target wavelength for the flexible substrate was set to 10 micrometers. Initial tests show that the Nantenna design can be translated to a polymer substrate, but further experiments are needed to fully optimize the characteristics. The proof of principle of optical nanoantennas can be realized in radio frequency range. High permittivity dielectric particles can be used to simulate silicon behavior at optical frequencies. This allows to perform experiment at microwave in order to predict Nantenna behavior at optics. Economics of Nantennas. Nantennas are cheaper than photovoltaics. While materials and processing of photovoltaics are expensive, Stephen Novak estimates the current cost of the Nantenna material itself as around $511 USD M2 in 2008. With proper processing techniques and different material selection, he estimates that the overall cost of processing, once properly scaled up, will not cost much more. His prototype was a 30 by 61 centimeters of plastic, which contained only 60 United States cents of gold in 2008. With the possibility of downgrading to a material such as aluminum, copper, or silver. The prototype used a silicon substrate due to familiar processing techniques, but any substrate could theoretically be used as long as the ground plane material adheres properly. Future research and goals. In an interview on National Public Radio's Talk of the Nation, Dr. Novak claimed that Nantennas could one day be used to power cars, charge cell phones, and even cool homes. Novak claimed the last of these will work by both absorbing the infrared heat available in the room and producing electricity which could be used to further cool the room. Improving the diode is an important challenge. There are two challenging requirements: speed and nonlinearity. First, the diode must have sufficient speed to rectify visible light. Second, unless the incoming light is extremely intense, the diode needs to be extremely nonlinear, in order to avoid reverse bias leakage. This assessment assumed that the antenna was a directional antenna array pointing directly at the sun, a rectenna that collects light from the whole sky, like a typical silicon solar cell does, would need the reverse bias current to be even lower still, by orders of magnitude. There are special diodes for high speed, and there are special diodes for high nonlinearity. But it is quite difficult to find a diode that is outstanding in both respects at once. To improve the efficiency of carbon nanotube-based rectenna. Low work function. A large work function difference between the MWC and T is needed to maximize diode asymmetry, which lowers the turn-on voltage required to induce a photoresponse. The WF of carbon nanotubes is 5 electron volts and the WF of the calcium top layer is 2.9 electron volts, giving a total work function difference of 2.1 electron volts for the MIM diode. High transparency. Ideally, the top electrode layers should be transparent to allow incoming light to reach the MWC-NT antennae. Low electrical resistance. Improving device conductivity increases the rectified power output, but there are other impacts of resistance on device performance. Ideal impedance matching between the antenna and diode enhances rectified power. Lowering structure resistances also increases the diode cutoff frequency, which in turn enhances the effective bandwidth of rectified frequencies of light. The current attempt to use calcium in the top layer results in high resistance due to the calcium oxidizing rapidly. Researchers currently hope to create a rectifier which can convert around 50% of the antenna's absorption into energy. Another focus of research will be how to properly upscale the process to mass market production. New materials will need to be chosen and tested that will easily comply with a roll-to-roll manufacturing process. Future goals will be to attempt to manufacture devices on pliable substrates to create flexible solar cells.